In this lecture, we'll discuss a potential problem that may appear when we do a linear regression model and we have more than one explanatory variable. This problem is called multicollinearity. So we will discuss a little bit about what this problem is, what we can and cannot do about it, and the consequences when we have the multicollinearity problem. So the setup is the linear regression model, and all we need to describe it is this linear regression model with random sampling. We need to have k at least at 3. So we need to have at least 2 explanatory variables. With one explanatory variable, multicollinearity can never be a problem. I will focus on 2 explanatory variables in this lecture. That's just to make the examples and so on a little bit simpler. And it is enough to have 2 explanatory variables to describe the multicollinearity problem. But we could easily have more explanatory variables, and I'll say a few things about that at the end. So here's my linear regression model. We view it as a data generating process, and by doing simulations we can develop our intuition about this model and also about the estimators that we use to estimate the unknown beta parameters. So let's see how we typically do this simulation study. We set beta parameters to be something, just chosen here 0, 1, 1, and we set the standard deviation of the error term to be something. Then we simulate data for the explanatory variable, and in general we don't really care about how we simulate that. And the reason is that all of econometrics is us saying things about the model conditionally on x, given the specific data that we observe for x. So we could easily just do something like norm dot imb rand, and we can simulate from 0, 1, for example. Then I copy this down. Let's say we have 15 observations, and I copy it over here. So I have now simulated my x data. To simulate my error terms, we typically do something similar. Norm.imb rand. For the error term, we have to put a 0 here if we want the explanatory variables to be exogenous. That's not important for the x data. That could be any expected value you like. And we put sigma here, b $4, and that will keep the variance of the error term constant. So pull this down, and from that we have our data generating process for y, which is then just actually, before I do that, let's just rename these because we want to start naming the x variables by x2 and then x3, skipping x1, and that's because we want the intercept also. So now we can do equal $1, that's beta 1, plus $2, that's beta 2, times d2, that's x2, plus $3, that's beta 3, times e2, and add to that the error term in f2. So that's the simulated value for y. Copy this down, and if I estimate now the parameters, we have 3 of them, k is 3, mark up 5, do linnest, the y's, the x's, the 1 and 1 for statistics, and we have Remember the reverse order. This is my B3, B2, and B1. I have done the simulations now completely according to the Gauss-Markov assumptions. So this will be an unbiased estimator of this will be an unbiased estimator of that, and this will be an unbiased estimator of the zero. So there is one special aspect of this simulation that I want you to pay attention to, and that's the following. So when I drew a random number here to simulate the first observation for x2, then to get the second observation for x2, I just used the fill handle to copy this formula down. Excel will then put the same formula into this cell, and it will therefore draw a new random number from exactly the same distribution. And the way that random numbers are simulated in Excel is so that these will be independent. So this number here is drawn from a random variable which is independent of this one. That's exactly what we want because we do assume random sample, remember? So anything related to the first observation should be independent of anything related to the second observation. These are all drawings from independent random variables. So here comes the important part. We took this formula and we copied it over to E2. Now that will of course also make these two numbers drawings from independent random variables. This is not something that's required by the Gauss-Markov assumptions and by random sampling. As a matter of fact, it's typically very unlikely to be true when we look at the random sample. To discuss a concrete example, let's say that this is investment. We're trying to explain investment, and let's say that this is for country I. So we have data for a number of countries. More specifically, it could be investment as a proportion of GDP. Let's say we want to explain investment using interest rate, and we want to use, let's say, the long run interest rate, perhaps the 10-year interest rate. It's not so important. And we want to also use a short interest rate, maybe the monthly interest rate. And the reason for doing this regression would then be to see if it's the long rate that affects investment, or it's the short rate, or perhaps it's both. And then to figure out which one has the strongest effect on investment. So in this setting, would it be reasonable to assume that the long and the short rate are independent? And the answer to this question would certainly be no. If a country has a high long rate, higher than other countries, it will also tend to have a high short rate and vice versa. So these explanatory variables will certainly be dependent. And this is precisely the issue that we will investigate. What does this dependence do to our results? The way I have simulated my data now, I cannot investigate this issue because I have simulated the data so that x2 and x3 are completely independent. That's the perfect case for doing data analysis. If you want to make the OLS estimator happy, then do simulations with independent explanatory variables. It will make life much easier for the OLS estimator to estimate the parameters. So the first sub-issue we need to investigate before we can investigate multicollinearity and what problems that causes is how are we going to simulate data such that there is actually dependence between x2 and x3. It's a very important topic because more and more of econometrics is done using simulation methods, and being able to simulate the data that has some dependence is important. So we'll have a look at that. Turns out that there are many ways that you can simulate data such that you introduce dependence between x2 and x3. I will do something very simple. I'll introduce a parameter here that I'm calling called delta. And it's just for this particular simulation study, so it's not a new symbol introduced into econometrics. And this delta will be take a value between 0 and 1. So when it takes 0, then x2 and x3 will be completely independent. And when it takes the value 1, they will be 100% dependent. And any value in between, you will have some dependence. And the strength of the dependence will be measured by this delta. So let's set it to say 0.5, the halfway in between case. So what I will do is I will change my x3 so that it is determined to be 50% equal to x2 and 50% equal to this random number from the normal distribution. So I will just change it to the delta value that we have in B6, so $6 multiplied by the x2, 50% of the x2 plus the remaining 50%, 1 minus $6 times something which is completely independent of x2. So you can see that when I set delta to 0, then the first term, delta times b2, will go away, and we will return to what we just looked at, the case when x2 and x3 are completely independent. And the other extreme, when delta is 1, then x3 will become exactly equal to x2. So complete dependence in that case. So we can do that, this. So note that these two are now not independent. And that is simply because this one is partly determined by this one and partly by something random. So that will make them dependent. These two are independent and these two are independent. Because this one only depends on that one and something random, and this one only depends on that one and something random. And since these are independent, these two will be independent as well. So we still have random sampling, but we have dependence between the explanatory variables. For this case, it's actually not difficult to show that the covariance between these two random variables is exactly delta. So delta will determine the covariance between them. Because of random sampling, the covariance between these two are delta as well, and so on. Since the covariance is the same between every two pairs, the sample covariance will actually then be a good estimate of the true covariance. So if I do covariance sample and I put this one and this one, then this will be an estimator of the true covariance 0.5. I have very few observations, so it's not going to be very good, but if you have a look at it and I F9 a lot, then it probably seems reasonable that 0.5 is in the middle of those numbers. If I take this delta down to 0, I again make them completely independent, because now x3 does not depend at all on x2 but only on this random number, And if you now look at the sample covariance, it will on average be 0. Plus and minus with equal regularity. And we can look at the extreme case. When I set it to 1, then you can see that these two become equal. Then there's a perfect dependence between x2 and x3. For this case, the sample covariance will be equal to the sample variance 1, and F9ing this, you'll see that this is on average now 1, even though it's typically pretty far from 1 because we have so few observations, which doesn't really allow the sample covariance to estimate the true covariance particularly well. This example, this simulation study, is a perfect example to describe and illustrate multicollinearity. So here are some definitions. We'll begin by talking about something called perfect multicollinearity. And we talk about perfect multicollinearity if one of the explanatory variable is an exact linear combination of the rest of the explanatory variables, then we have perfect multicollinearity. In this case, we will have perfect multicollinearity when delta is 1. When delta is 1, then x3 is exactly equal to x2. So a perfect linear combination of x2. This is perfect multicollinearity. If I just change it to something less, then it's no longer perfect multicollinearity, because as you can see, the x2 and the x3 are now no longer exactly equal. If you have more than 2 explanatory variables, then we say that we have perfect multicollinearity if one of them, let's say x3, can be explained as a linear function of the other one. Maybe I have an x4 as well. And if x3 is some linear combination of x2 and x4, then we have perfect multicollinearity. In the sense of our example, what would perfect multicollinearity be here? Well, that would be if the data for the long run interest rate was exactly the same as the one for the short rate. So if I had data and all my long run interest rates were the same as the short run interest rates, I would have perfect multicollinearity. It would also happen if the difference between them were constant for all countries. So if the long rate was say 0.1 above the short rate for every country, then I would have a linear combination as well and perfect multicollinearity. So here's an important result. With perfect multicollinearity, OLS will actually break down. We can't really see that because we haven't written the equations for the OLS estimates in the case of several explanatory variables. But if we had done that, then we would be able to see that in the formula for B2 and B3, we would actually end up with something like 0 over 0. Now, in the case of several explanatory variables, you actually turn to matrices instead, and the corresponding result is that to do OLS, you need to invert a specific matrix. And when you have perfect multicollinearity, this matrix will not have an inverse. So you just simply cannot calculate the OLS estimator. So if I change this now to 1, what I'm saying is that OLS can now not be calculated. And it seems like what I'm saying is not true because, as you can see, Excel has actually done it. Well, in fact, it hasn't. It's just being overly clever here. What it has done is that it has actually determined that you have data that's perfectly multicollinear. And it has simply kicked out one of the variables. It has simply removed, in this case, the x2 variable. That's why you actually have zeros here. Those are not estimates. Those are just saying that, okay, let's get rid of the x2 variable because it's perfectly correlated with x3, and then we can do OLS. All right, so if you have a complete disaster at delta equal 1, when you have perfect multicollinearity, it would not be too surprising, I guess, to claim that you have problems when delta is close to 1. That is, when you're close to perfect multicollinearity. So we're simply going to call that multicollinearity. So multicollinearity will be the case when one explanatory variable is close to be equal to a linear combination of the rest of them. So in our simulation study, perfect multicollinearity, multicollinearity, and no multicollinearity whatsoever. Here OLS is very happy, here OLS is really sad, and here OLS breaks apart completely. It's very important to realize that multicollinearity is a matter of degree, not kind. You cannot say that we have multicollinearity or we do not have multicollinearity. It is a matter of how much we have. So what we can say is that this case of multicollinearity is worse than this case. But it's not possible to give a limit, let's say maybe here. Above this you have multicollinearity and below it you don't have. You cannot do that. And this is one of the issues that makes multicollinearity a little bit difficult to work with. So what people tend to do, because in a real econometric setting, this delta is obviously not known. All that's known is the x data. What people tend to do is to calculate this guy. This is the sample correlation. Remember, that's just the sample covariance divided by the sample standard deviation of x2 times the sample standard deviation of x3. Now this sample correlation will of course depend on delta. So if I make this high, like in this case, the sample correlation will come out to be pretty high as well, close to 100%. If I F9, you see that it's typically above 99%. While if I take it down, maybe even to 0, the sample correlation comes out to be pretty low, typically around 0. So the higher the sample correlation, the more likely this delta value is high, and the more dependence we have between x2 and x3. So what's common to do is then simply to look at the sample correlation between the explanatory variables. If that comes out to be close to 1 or -1, because we could also have the case that there is a linear relationship between them, which is negative. So if this happens, then we say that we probably have multicollinearity in the linear regression model. But unfortunately, there is no sort of real cutoff point here. It's just a question of the closer the sample correlation is to 1, the worse is the multicollinearity problem. So to investigate this issue a little bit further, let's look at some of the consequences of multicollinearity. And this is the big problem. If you have multicollinearity, then what will happen is that the estimated variances, as well as the true ones, they will be very high. In words, what that means is that OLS will have a very hard time figuring out what the true betas are. So check out this example. Delta is 0. I have no multicollinearity whatsoever. OLS has a really good time. It can give you very small standard errors, 0.05 for both B1 and B2. If I print the t values down here, let's do t values. Remember, the t values are just the point estimate divided by the standard error. So it's this one divided by the standard error. And well, let's remove this one for the intercept. Remember, the critical t-values are somewhere around between 2 or 3 or something like that, and these are huge. So it's very easy here for OLS to figure out that beta is strictly greater than 0. If you've done confidence intervals, you'll also see that it's pretty tight. OLS is happy because there is no multicollinearity at all. So let's increase this one. Let's increase the correlation covariance between x2 and x3. And let's see what happens. I take it up to in between 0.5. Still pretty happy, but the standard errors are now larger, like 0.1 on average. So t-values has gone down, but they're still very significant. So OLS is still pretty happy. Take it up to 0.9, like this, and OLS is beginning to become very unhappy. You can see that the standard errors has increased a lot, and now suddenly in some cases it cannot even tell whether beta 2, in this case beta 3, is significantly different from 0. This t-value is not significant. So we're making life very hard for OLS right now. And let's do this in the extreme, 0.99. Now there is enormous multicollinearity. And you can see what happens to the standard errors. They've become huge. It's really, really hard for OLS to do anything. You can see that the confidence interval for B3 is something like 3.4 plus minus a standard error of 5 and a t-value of, I don't know, 2.5. So the confidence interval is huge. It's still correct. It's still true that the true value is in the confidence interval with the 95% probability if that's the one you choose. And it's still true that we'll reject the null hypothesis incorrectly in 5% of the cases if that's your level of significance. The problem is that the confidence intervals, they become very large and the power of the test very small. So why has this happened? Well, the answer lies sort of in the interpretation of, let's focus on beta 3. Beta 3, remember, measures the effect on the expected value of y when I increase x3 by 1 unit, keeping x2 constant. Well, it's really hard for OLS to figure out the answer to this question because it doesn't really have data that can help it do that. If you increase x3 by 1 unit, you would want some other data where x2 doesn't increase, but they are so highly correlated that whenever x3 increases, x2 increases by about the same amount. So it becomes very difficult to distinguish between the effect of these two variables. Is it x2 that's causing the effect, or is it x3 that's causing the effect? It's almost impossible to tell because they're almost always the same number. Going back to this example, you would expect the long rate and the short rate to be very highly correlated. And that means that if you try to run this regression, the standard errors of B2 and B3 will be very large. And this will be the case in general. You have to be careful with your regression model. Try to think about the explanatory variables and try to figure out if multicollinearity will be a problem by simply considering this issue. Is it possible that one of my explanatory variable is really well defined by my other explanatory variables? If that's the case, then you likely have a multicollinearity problem. Here's the second important point about multicollinearity. So when we have multicollinearity, the variances tend to be high, which means that each individual x variable on its own may be really insignificant, but together they can be highly significant. So when they work together, they can actually create a very good fit with the high R square, but on their own, they're typically then insignificant. You can see that pretty clearly in this simulation study. So on their own, they're highly insignificant. The t-values are not significant. But if you look at the R square, it's 99.6%. So together they do an excellent job. But since we don't know which one is doing the excellent job because they're so collinear, they will be insignificant together. If I do an F test and test the joint significance, that beta 2 is 0 and beta 3 is 0, in this case, that will certainly be rejected. Together, they are highly significant. Individually, they are not. And this is really what you should look out for. If you find in your results precisely this thing, high R square, very nice fit, but insignificant t-values, then the likely cause of this is multicollinearity. So finally, what can you do about multicollinearity? So the answer is that there is really no cure for multicollinearity in the sense that we can't just fiddle around with this and come up with other estimates that are better. The problem really lies in the fact that the data doesn't have the answer we're looking for. I am trying to figure out the effect that x2 by itself has on y, and the data doesn't have that answer for me. So it really doesn't matter what I do to the data will never give me an answer. So no matter how much I torture this data, it's just not going to be able to confess. That means that your only way out of this is to look at other data, maybe collect more data, for example, or simply to drop the problem altogether. Maybe you can simplify the problem. Perhaps you have a regression model which included both short and long interest rate and some other variables. Then perhaps you can drop one of them. That, of course, is not something that you can do if the purpose of the study is to investigate whether it's the short or the long run interest rate that determines investment.